Hi all, in this video I'll cover multidimensional arrays. A multidimensional array is an array of 2 or more dimensions. Multidimensional arrays are ideal for representing structured data, such as grids, tables, game boards, cubes, and n-dimensional matrices. Here I have an illustration of a grid or a table. It has 2 dimensions, there's 3 rows and 4 columns. Let's check out how we would represent this in C or C++. On the right, I create a 2-dimensional array named matrix. The first dimension has a size of 2, while the second dimension has a size of 3. As you can see, every dimension is defined by a pair of brackets with a size for that dimension. So here the first dimension is defined by the first pair of brackets, and it has a size of 2. The second dimension is defined by the second pair of brackets. It has a size of 3. If I wanted to add a third dimension, I could simply add another pair of brackets and set the size for that dimension. And for any additional dimension that I want to create, I simply keep adding another pair of brackets with an integer that defines the size for that dimension. Now, as mentioned, this array is 2-dimensional. It has 2 rows and 3 columns. The first row holds the elements 14, 73, and 22. The second row holds the elements 58, 16, and 49. This matrix is also illustrated by the table on the right. There are 2 rows and 3 columns. The first row has an index 0 and the second row has an index 1. And for the columns, same idea. The first column has an index of 0, the last column an index of 2. Let's see how we can access the elements in this 2-dimensional array. Now the same concept that we used for creating a new array we use when accessing an element in a multidimensional array. That is, for every dimension we write a pair of brackets and in between we specify the index that we want to access. Let's say I want to access element 14. 14 is located at index 0 for the first dimension and index 0 for the second dimension. Now in code, I write down the identifier of my 2-dimensional array, which is matrix, then a pair of brackets specifying the index of the first dimension and another pair of brackets specifying the index of the second dimension. So here in brackets 0 and 0. This will give me the value 14. Let's do another example. Let's say I want to access the value 16. 16 is located at index 1 for the first dimension and index 1 for the second dimension. So again, I write down matrix, pair of brackets with 1, another pair of brackets also with 1. This will give me 16. And let's do one last example. Let's say I want to access 22. 22 is located at index 0 and index 2. So in code, I write down matrix, pair of brackets with 0 and pair of brackets with 2 for the second dimension. This will give me 22. Now let's take a look at a code example. In this program I define 2 constants. The first constant represents the number of rows, while the second constant represents the number of columns. Then I have a function prototype that defines 2 parameters. The first parameter is a matrix where the size of the first dimension is defined by the second parameter. The size of the second dimension is hard-coded to 2. Unfortunately in C, when you pass in static arrays to functions, only the first dimension can have a variable size defined by another parameter. All the other dimensions have to be hard-coded. So with that, let's jump into the main. Here in the main I create a 2-dimensional array with 4 rows and 2 columns, and I initialize it directly with these values. Then I pass the array to the print matrix 4 columns function. And again, I just specify the identifier of the matrix. There's no additional brackets needed when passing in any array to a function. The second argument is the row count constant that represents the size of the first dimension. This function is implemented below the main. Inside the function, I have a for loop that iterates over the rows. So starting at row 0, row less than row count, and row plus plus. And then column initialized to 0, column less than 2, and column plus plus. And in each iteration, I output matrix at row and column. This will give me the element at this position in the matrix, and I print it out. I add a line break, and at the end I simply return from the function. Let's run this program. Now here you can see the output. This exactly outputted what I defined inside the main. There are 4 rows and 2 columns. Now let's take a look at variable length arrays. Now I've updated my program to use multidimensional variable length arrays. This only works with version C99 and above. Now at the top I declare a function prototype named printMatrix that defines 3 parameters: the row count, the column count, and a 2-dimensional array named matrix with row count and column count. So the sizes of both dimensions are now flexible, and they are defined by the first 2 arguments. Inside the main, I declare 2 variables that define the row count and the column count. Then I define a variable length array of 2 dimensions using the row count and column count variables. Then I use 2 nested loops to initialize all the elements in this 2-dimensional array. I declare a variable named base initialized to 1. This represents the base value of the very first element in this 2-dimensional array. All the other elements will get an updated value by incrementing base by 1. Now here I have 2 nested loops. The first loop iterates over the rows, while the second loop iterates over the columns. Inside these loops, I have a statement where I access the matrix at row and column, and then I assign the current base value. After I assign it, I increment base by 1. And finally, I call the printMatrix function. I pass in the value of row count and the value of column count, and I pass in the matrix. Let's run this program. As you can see, the program outputted my 2-dimensional array, and I started with the base value of 1. I incremented 1 to 2, 3, 4, 5, 6, 7, 8. Let's add a breakpoint to better understand what's happening here. Now I start this loop with row being 0, and column being 0, and base being 1. So at matrix, row 0, column 0, I initialize to 1. Then I increment the base to 2, and I assign it to row 0, column 1. When I increment column to 2, this condition is false. I end the nested loop, I go back to the outer loop, and here I increment row from 0 to 1. Then again I start the nested loop, I initialize column to 0, and row is now 1, but column 0, and base is 3. I increment base to 4, I increment column to 1, so now I access matrix at row 1 and column 1, and I assign 4 to it. I increment base to 5. I'm done with the second row now, so I increment row from 1 to 2, and again the nested loop starts back at 0. So now I access the matrix at row 2, column 0, and I assign 5 to it. And this continues until all elements of every row are initialized. When I continue, I can see the successful output. With that, let's take a look at dynamically allocated arrays. I first include standardlib.h so I can call the malloc and free functions in my program. Then I declare 3 function prototypes named createMatrix, printMatrix, and freeMatrix. Inside the main, I declare 2 integer variables named row count and column count that specify the sizes of the first and second dimension of my 2-dimensional array. I pass these variables to the createMatrix function. This will create a 2-dimensional array. This function call returns back a pointer to an integer pointer. Next, I check if the matrix was successfully created, and if so, I call the printMatrix function to print the matrix to the console. Then I call the freeMatrix function to free up that memory. If memory allocation failed, I print out an error message, and then my program ends. Let's take a closer look at the createMatrix function. The createMatrix function defines 2 parameters named row count and column count that specify the size of the matrix. I have an integer variable named base initialized to 1. This represents the value of the very first element in the matrix, and all subsequent elements will be incremented by 1. So I start with element 1, then element 2, element 3, and so on. The second statement is a call to malloc. You should already be familiar with malloc from my other video on dynamically allocated arrays. Now for this malloc function call, I pass in row count, which is the size of the very first dimension, multiplied by the size of each element. And the element type is integer pointer. This function call gives me back a pointer to an integer pointer. Now you may wonder why I'm using integer pointer instead of just integer. Because in my two-dimensional array, I really want to store integers, not integer pointers. Now in order to understand this, we really have to think in terms of one-dimensional arrays and how they are represented in code. When I have a variable that represents a one-dimensional array, that variable is really a constant pointer to the very first element of that array. And this statement here, I just create a one-dimensional array of integer pointers. This represents the first dimension of that array, and each integer pointer will later point to a row in this two-dimensional array. Take a look at this illustration at the top right corner. Here I have my matrix variable, that is the pointer to an integer pointer, and the malloc function creates this vertical array right here. Essentially, it's an array of integer pointers, and each integer pointer in that array points to a row in the matrix. So initially, after making this statement, I have an array of integer pointers, but all these pointers just point to null or some garbage memory. They are not initialized yet. After calling malloc, I check if memory allocation failed. If so, I return null. If the array was allocated successfully, I use a for loop to iterate over the rows of that array. Essentially, I iterate over this vertical array right here, starting at index 0. So at row 0, I call the malloc function, and this time I pass in column count multiplied by the size of an integer. This allocates a one-dimensional array that represents the very first row up here. And then I assign this array to the very first row. I check whether memory allocation failed, so if matrix at row is null. If so, I return null, I'm done. Otherwise, I iterate over this very new array, starting at column 0, column less than column count, and column plus plus. And I initialize it to my base value. And after the initialization, I increment base by 1. So accessing matrix at row being 0, then column being 0, I essentially have this element right here. I initialize it to 1. I increment base by 1. I increment the column by 1. So now column is here. Base is 2. So I assign 2. I increment base to 3. I increment column by 1. So column is now 2, which is index 2. Base is 3. I assign 3. I increment base. Go to the next column. I assign 4. And then my loop ends. Now I increment row by 1. Call again malloc for row 1. So I allocate this second array here, the second row. And again, I use a for loop going through all the columns, starting at column 0 and continuing with my base value. So I assign 5, 6, 7, 8. The nested for loop ends. I increment row by 1. Now I'm at this integer pointer. I allocate a new array, and using the for loop starting at column 0, going through all the columns and assigning 9, 10, 11, 12. Done with the nested loop, incrementing row to 4. So now I matrix at index 4, which is the last element in this first array. And again, I allocate memory for an additional array, which is the last row here, and continuing to initialize the elements to 13, 14, 15, 16. Then I increment row to 4. So 4 is not less than 4. So the condition is false. I end the outer loop and I return the pointer to this two-dimensional array, which is essentially a pointer to an integer pointer right here. Let's go back to the main. Here I have the pointer to my matrix. I check if this was successful. Let's assume this was successful. I call the print matrix function. And the print matrix function expects a pointer to an integer pointer along with row count and column count. This simply is a nested loop going over all the rows and all the columns. So it goes to the first row, over all the columns, increments the first row, going over all the columns, next row, all the columns, and final row, all the columns. And finally, going back to the main, after this function call, I call free matrix and passing in the matrix and the row count. And what you see here is there's not just a single free call, but I have to call free multiple times. Essentially, I have to free up every array in this matrix and also the final array right here. So I'm doing this by using a for loop starting at row 0. So I'm iterating over this vertical array right here. Then I call free on matrix at row. So I call free on this one, and this frees up the very first row right here. This is my very first array. Then I increment row by 1. I go to the second location. This is my pointer here. And I say free up the memory where this pointer is pointing to. This clears the memory for the second row. I increment row by 1. I'm right here. I call free again. This frees up the memory represented by this array. And then for the final one, I also call free. This frees up the memory for my last row. Then I'm done with my loop. And then I call free on the matrix, which frees up the memory of this array that held all the integer pointers. Let's run this program. So you can see the output is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now in this illustration I had one additional row. Then I have here, this was because I had row count initialized to 3, but I could quickly update it to 4. So with 4 I get the exact same array that I have up here. Now let's take a look at when to use what type of multidimensional array. This table explains what array type to use when. Your first choice should always be static arrays. Use static arrays when the size or the size of all dimensions of your array is known at compile time. Here's an example of what static arrays look like. So static arrays, you hard code the dimensions with integers, or you can use constants. And these arrays are allocated on the stack. That means memory is managed for you. You don't have to allocate memory. You don't have to free up memory. The second choice are variable length arrays. Always use variable length arrays when the size depends on user input. That is when you don't know the size of the array or any of the dimensions during compile time, but you only find out during runtime. Here again is a short code example. You use integer variables for the dimensions, and you use these variables when you create a new array. These arrays are also allocated on the stack, so memory is managed for you as well. Note that these types of arrays only work in version C99 and above. And finally, dynamically allocated arrays. Use dynamically allocated arrays when you want to create an array inside a function and return that array from that function. Here's an example of how to create a two-dimensional dynamically allocated array. This type of array is allocated on the heap. That means you have to manage memory. As you can see, you have to call the malloc function to allocate memory. And when you no longer use this memory, you have to call the free function to free up that memory. I hope this gives you a good idea of how to use multi-dimensional arrays and when to use what type of array. Thank you for watching.